Hello viewers, I Dr. Mala Das Sharma welcome you to my video number 134 of my channel MALACHEMPHILIC, and this video is the episode number 73 of Chemical Thermodynamics, where the topic is multi-component phase equilibrium, boiling point elevation. So let's start. So what is boiling point? Boiling point, we know that is the temperature at which vapor pressure of the liquid becomes equal to the atmospheric pressure. Say for water, boiling point of water is 100 degrees centigrade. What does it mean? It means that at 100 degrees centigrade, vapor pressure of water becomes equal to atmospheric pressure, that is 1 atmosphere pressure. Okay, and the boiling point is the temperature where vapor phase and the liquid phase are in equilibrium. They remain in equilibrium. Okay. Now, elevation of boiling point. In my last video, I have discussed that when a little amount of non-volatile solute is added to a pure solvent, then vapor pressure of the solvent decreases. Why? Solute is non-volatile, then that non-volatile solute, they occupy some of the portion at the surface of the pure solvent. So from those portion, pure liquid or pure solvent cannot get vaporized. So amount of vapor form is less. As the amount of vapor form is less, that pressure exerted by the vapor on the surface of the liquid or the vapor pressure of the pure liquid or solvent decreases. As this vapor pressure decreases due to addition of non-volatile solute, then what will happen? The vapor pressure in the solution becomes equal to the atmospheric pressure at more higher temperature. So that at higher temperature, more amount of vapor will form, then the vapor pressure will become equal to the atmospheric pressure. So what is the net result? That this liquid boils at a higher temperature. So whenever you are adding a non-volatile solute to a pure solvent, then the boiling point of the pure liquid or the pure solvent increases. So that liquid or that solvent boils at higher temperature. That is known as the elevation of boiling point due to addition of non-volatile solute. So since the addition of non-volatile solute lowers the vapor pressure of the solvent, solution always has a lower vapor pressure than the solvent, and hence it must be heated to higher temperature to make its vapor pressure equal to atmospheric pressure, with the result the solution boils at a higher temperature than the pure solvent. What just now I explained. Now this will derive this equation for this elevation of this boiling point. Okay, now look at here. This is the curve for the vapor pressure versus temperature. This curve, it is for the pure solvent, and this is for this dotted curve for the solution, that means which is prepared after addition of little amount of non-volatile solute. Now you see at temperature TB, this vapor pressure of the pure liquid is equal to the atmospheric pressure. So TB is the boiling point of this pure solvent or the pure liquid. Now when you have added little amount of non-volatile solute, then look at here, look at this solution curve. At temperature TB, it is not equal to atmospheric pressure. Atmospheric pressure is higher. That means this vapor pressure is less. So for the solution, this vapor pressure equal to atmospheric pressure here, that is the temperature, say it is T. This is T. So it boils at a higher temperature. Okay, and this difference of this boiling point, that means boiling point of the solution which boils at a higher temperature minus boiling point of the pure solvent, that is known as the elevation of boiling point. Okay, so boiling point, TB is the boiling point of the pure solvent. T, if we consider boiling point of the solution, then difference between the two is the elevation of boiling point, which is equal to T minus TB. Okay, now we see this derivation of this elevation of boiling point. What is the equation? See, chemical potential of the solvent A in the liquid phase. I told you at the boiling point, liquid and vapor phase are in equilibrium. So we know this equation. Chemical potential of any component, here it is solvent in the liquid state, that will be is equal to chemical potential at the standard state in the liquid form plus RT activity of A. Okay. So mu star A, it is the chemical potential in the standard state. Standard state means pure liquid. Okay. Now, chemical potential of A in the vapor phase, what is that one? Vapor phase, it will be equal to the standard state only. Why? Because here the solute is non-volatile. So, as the solute is non-volatile, so no solute vapor is formed. So, vapor is formed only for the pure liquid. Okay. So, here this chemical potential in the vapor state is equal to the, it is the solvent, A indicates the solvent, is equal to the chemical potential at the pure state. Okay. So here the reason is, since solute is non-volatile, solute is non-volatile, non-volatile, only the solvent vapor is present, solvent vapor is present in the vapor phase, because solute is not able to form the vapor. So only solvent vapor is there. So it is the pure solvent, chemical potential of the pure solvent. So at the boiling point, this chemical potential of the liquid phase and vapor phase are equal. Okay, that is the condition. So, because we know that at equilibrium, chemical potential of the substance must be equal in all the phases. Okay, so this we can write. So now chemical potential in the liquid phase is mu A star liquid phase plus RT ln activity of A is equal to chemical potential in the vapor phase, means that is the chemical potential of the pure solvent in the vapor phase. So from here we can write RT ln A activity of A is equal to this minus this, chemical potential in the pure state in the vapor phase minus in the liquid phase in the pure state. So RT ln activity of A. Now here we know that this chemical potential of the pure substance is equal to the molar Gibbs free energy, that we know. Already I told you in earlier videos. So we know that. Why we have write these things? See, here I'll write, since chemical potential of pure substance, chemical potential of pure substance is equal to molar Gibbs free energy. Gibbs free energy. Okay, so I can write here that is molar Gibbs free energy in the vapor phase minus molar Gibbs free energy in the liquid phase. So ln activity of A, earlier equation you have seen that RT was there, so it divided by RT. So molar Gibbs free energy in the vapor state minus liquid state, that is the nothing but the Gibbs free energy of vaporization. That means Gibbs free energy change during vaporization. Delta Gm vaporization divided by this is RT. Now differentiating this equation with respect to temperature at constant pressure. then what we will get? It will be ddt of ln activity of A is equal to ddt of this term, that is Gibbs free energy or molar Gibbs free energy of vaporization, delta Gm vaporization divided by RT. Okay, so delta Gm vaporization is the free energy of vaporization per mole of the solvent. Okay, now if you differentiate this one, then look at here, ddt of ln activity of A is equal to 1 by R. This R you have taken this side. Okay, now there are two terms. One is 1 by T and another one is delta Gm vaporization. Okay, there are two terms. How to differentiate? That is first function 1 by T, then differentiation of the second, that is dole of delta Gm by dole T at constant pressure, plus second function, that is delta Gm vaporization into differentiation of the first. Differentiation of the first means differentiation of 1 by T, that means T to the power minus 1, ddt of T to the power minus 1. T to the power minus 1 means what will be the answer? T to the power minus 1, that means T to the power minus 2 and minus. So minus 1 by T square. This is the answer. So ddt of ln activity of A, that is equal to 1 by R, then 1 by T. Okay, this one. See, look at here. We know that here I'll write dg is equal to vdp minus sdt. So if we differentiate with respect to temperature at constant pressure, so dole G by dole T at constant pressure, that is equal to minus S. So this one we know. Okay. So in this place, in place of this dole of delta Gm by dole T at constant pressure, I can write that minus this delta Sm, that is entropy, molar entropy of vaporization. That means entropy change during vaporization per mole of the solvent. Molar entropy change of the vaporization, and this is this one minus delta Gm vaporization divided by T square. Okay. Now next, so ddt of ln A is equal to minus 1 by R, minus we have taken common. So delta Sm, molar entropy of vaporization per mole of the solvent divided by T, plus delta Gm vaporization divided by T square. So ddt of ln activity of A is equal to minus 1 by R. This T square I have taken LCM. So what will happen? This T square divided by T, that means T delta Sm vaporization plus delta Gm vaporization by divided by T square. Okay. So once again the same line has come, ddt of activity of A minus 1 by R, the same thing. Okay. Now look at here. Here I have written delta Hm. We know that G is equal to, since G is equal to H minus Ts. Okay. G is equal to H minus Ts. So what we can write? G plus Ts, we can write it as G plus T is, we can write it as H, that is enthalpy. So G delta G plus T delta S. So delta G plus T delta S, that we can write it as delta H vaporization. Okay, that only we have written here. So ddt of activity of ln activity of A is equal to minus 1 by RT square, and in this place we have written delta Hm vaporization. This is the, what is this one? This delta Hm is the latent, that is the latent heat of vaporization per mole of the solvent. Okay. So this is, that is enthalpy of vaporization or latent heat of vaporization. Here I can write this delta Hm vaporization. This is molar enthalpy of vaporization, molar enthalpy of vaporization, or latent heat of vaporization per mole. Latent heat of vaporization per mole. Okay, so now I integrate this equation within the limit. So integration of d ln A, dt I am taking this side. So d ln activity of A, and this limit is A dot 1 to A2. That is A1 is the solvent state activity and A dot 2 is the solution state activity. Okay, is equal to minus delta Hm. This we are considering remains constant within the temperature range. Delta Hm vaporization divided by R, then integration of Tb to T. Solvent boiling point is Tb, solution boiling point is T. So 1 by T square dt. Okay. Then if we integrate it, then look at here. It is integration of ln activity of A. So it integration will be ln activity of A. So ln activity of A, upper limit A1, that is solvent activity, and this is A2, that is solution activity. Okay, that means activity of the solvent in the solution state, minus delta Hm vaporization by R, and then this one, this integration of 1 by T square dt. Okay, that result will be minus, already have shown you earlier, minus 1 by T, limit is Tb to T. So ln A2 is equal to delta Hm vaporization by R, then 1 by T minus 1 by Tb. Okay, then this minus got cancelled. So here ln A2 is equal to delta Hm vaporization by R. If you simplify this one, Tb minus T, and here it is T into Tb. Achha, Tb minus T. Tb minus T. T is the boiling point of the solution, which is greater than boiling point of the pure solvent. Tb is the boiling point of the solvent. So T minus Tb is the elevation of boiling point. Okay, T minus Tb. So here it is Tb minus T. So it is minus delta Tb. And it is TTB. Since the solution is dilute, so this T is almost equal to Tb. T is very close to Tb. So I have, instead of T into Tb, I have written Tb square. Okay. So this is the case. So ln A2 is equal to minus delta Hm vaporization by R Tb square into delta Tb. Here minus is there. Okay. Now ln A2 is the activity of the solvent in the solution state. That activity we can write activity coefficient into mole fraction. Activity coefficient of the solvent into mole fraction of the solvent minus same thing, minus delta Hm vaporization into Tb divided by RTb square. Now here this activity means solution is, as the solution is very dilute, here I will write, since the solution is very dilute, solution is very dilute. So here your activity of the solvent almost is equal to, mole fraction of the solvent is equal to this activity of the solvent. Why? Since this activity coefficient is equal to 1. Solution is very dilute. So activity coefficient is 1. So activity is equal to mole fraction. So here I have written this as the activity coefficient is equal to 1. So I have written ln xa is equal to minus delta Hm vaporization into delta Tb by RTb square. Then xa I can write 1 minus xb because one solvent and one solute, and we know xa plus xb. Xa is the mole fraction of the solvent, xb is the mole fraction of the solute. Xa plus xb will be equal to 1, so 1 minus xb, then same term minus delta Hm vaporization into delta Tb divided by RTb square. Okay, now if you expand this one, after expanding and neglecting the higher term, it will be minus xb is equal to minus delta Hm vaporization into delta Tb square divided by RTb square. Now xb minus minus will get cancelled. Now xp is equal to, you know that mole fraction of the solute will be number of moles of the solute divided by total number of moles, that is number of moles of the solvent plus number of moles of the solute, that is equal to delta Hm vaporization into delta Tb divided by RTb square. Okay, now here, look at here. Here it is Nb divided by Na plus Nb. But here I have written Nb divided by Na. Reason is saying since the solution is dilute, so your Nb, number of moles of the solute is much less than the number of moles of the solvent. So what we can write? That Na plus Nb almost equal to Na. Okay. So from here we can write delta Tb will be equal to Nb into RTb square divided by Na delta Hm vaporization. This is my equation number 1. Okay. Now see this one. Let weight of the solvent is Wa. So Wa gram of the solvent contains Nb moles of solute. So 1000 gram of the solvent contains Nb by Wa into 1000. That is the molality. Okay, number of moles present in 1000 gram of the solvent. So molality M is equal to Nb by Wa into 1000. So from here Nb is equal to molality into weight of the solvent divided by 1000, right? So now delta Tb, what we have seen here, delta Tb is equal to this equation number 1. So equation number 1, delta Tb is equal to Nb RTb square divided by Na into delta Hm vaporization, and Nb is equal to, just now we have seen, molality into weight of the solvent divided by 1000. So in place of this Nb, we have written this W M into W divided by 1000, remaining things as it is. So delta Tb will be equal to, now here you see this Wa is getting cancelled. So what is left over? Delta Tb is equal to M into RTb square divided by 1000 and look at here, it is delta Hm vaporization divided by molecular weight. Delta Hm vaporization is the latent, that is molar enthalpy of vaporization or latent heat of vaporization per mole of the solvent, divided by molecular weight means latent heat of vaporization per gram of the solvent. So here this delta Hm vaporization divided by Ma, this is the latent heat of vaporization vaporization per gram of the solvent. Gram of the solvent, and that we are taking it as small LV. So what we can write, m into RTV square divided by 1000 into small LV. Small LV is the latent heat of vaporization per gram of the solvent. So now this C R is constant, TB, that is boiling point of the pure solvent, constant, 1000 is constant, LV is constant, latent heat of vaporization per gram of the solvent. So this whole thing is constant. Okay. So RTV square 1000 LV we are taking is a constant KB. Okay, this Kb is the molar elevation constant of the solvent. So delta Tb is equal to Kb into m. So delta Tb proportional to m. Now from here, how can you define this Kb, molar elevation constant? When molality is equal to 1, m is equal to 1, delta Tb is equal to Kb. So what we can write? That molar elevation constant Kb, molar elevation constant, is the elevation of boiling point when molality of the solution is 1. So, hope you have understood. Thank you.